Today, I'm interviewing Max Hodak, an extraordinary founder, scientist, engineer, and investor at the frontier of neurotech. Max is the founder and CEO of Science Corp, where he and his team are developing breakthrough neural technologies, devices, and platforms. Today, science is focused on the PRIMA visual prosthesis, which literally restores sight in people with some forms of blindness. And they are also pioneering a biohybrid brain-computer interface, which I'm personally most excited about. On top of that, Science Corp is building software and hardware platforms to drop the cost of neurotech R&D, enabling other companies and a new generation of startups. Before Science Corp, Max co-founded Neuralink and Transcriptic, now Stratios. His work cuts across neuroscience, engineering, and philosophy, all united by the questions about how to expand human capability. This interview is part of a series on neurotech where we explore and discuss near and future breakthroughs, why they matter, and how they will benefit humanity. Let's dive in. What exactly is neurotech?
I mean, in some sense, neurotech is this incredibly broad idea because everything about our behavior is rooted in the brain. And so, I mean, there's some interpretation where social media and the iPhone is kind of neurotech. But I think when we talk about it specifically in the context of brain-computer interfaces, you're talking about mostly implantable devices, some wearables, but instead of, it's like if you've lost the ability to use your hands or use your eyes or use your ears, maybe we restore those sensory or motor capabilities? Can we bypass a broken nerve or a lost function? And there's some groups that are starting to look ahead and if you can understand really how does the brain do these things and how does the brain form percepts and how does it reason and how does it remember, then you could you can go from restoring to potentially extending.
Can you maybe start with a quick history of the neurotech field, recently, in the last few decades, just from your perspective?
A lot of what I consider brain-computer interface started in the 70s, the 60s and 70s. It was pretty quickly figured out that if you put an electrode in the brain of a monkey, if you got it to move a joystick, you could figure out how in the brain that was functioning. I mean, people have been doing this in humans really since the 90s. So in the mid-90s, the Utah array was invented, which is a very classic neural probe. It's these silicon needles that can be placed into the brain to record neural activity. And in the late 90s, early 2000s, people were decoding cursor control and basic keyboard control in humans. Now, that system is not really ready for prime time then. That probe in particular gets an immune reaction and it's a relatively small number of electrodes. It doesn't really match material properties of the brain in some of the ways that you want, but kind of more to the point, it had a connector that came out through the scalp. So there was a pedestal that was anchored to the skull and then a connector coming out through the skin. And the skin is a very important immune barrier. You really want the skin to be closed because if it's not, there's a risk that a bacteria could crawl down your connector and potentially into the brain, and then you're going to have a really bad time. And so a lot of the advancement over the last 10 years has just been miniaturizing the electronics and making them low power enough that they can be fully implanted and the skin can be closed. And this is, I think, the fact that this is possible now is something that's been built on the back of what we call the smartphone dividend, the fact that Apple and Samsung and others have poured tens of billions of dollars into building the modern electronics required to do this that then we get to take advantage of. But the neuroscience is really not that different from what's been understood. The basic neuroscience of motor decoding has been understood for decades. It's the advances in the electronics and the materials that have kind of, I think, led to the modern wave of new BCI. BCI originally, I'd say, came out of neuroscience. And the field of neuroscience is concerned with things like what are brains and how do they work? There's a bunch of circuits in the brain, some that deal with affect or attention or motivation or memory or reasoning or motor planning or whatever. And if you want to understand what's going on in there, then at some point you need to be able to see into the brain. You need to be able to record and detect all this activity. And the endeavor of neuroscience has been placing wires into the brain to record neural activity basically since the discovery of neurons. And so BCI originally, I'd say, came out of neuroscience. And the tools that were being used in BCI were essentially neuroscience tools. And I think only now are we starting to see some new types of BCI probe approaches that could be used to understand things about the brain, but really begin to diverge a little bit. So, for example, the biohybrid work that we're doing is, I think, a great example of this. With the biohybrid probes, we don't place a wire or an imaging system or a fiber into the brain. What we do is we load a device with living cells, with biological neurons, and then we make it so the cells don't go anywhere. They're stuck in the device, and then we engraft this into the brain. So the living cells project new biological connections. They form new chemical synapses with the host brain. But they do this in a perfectly biocompatible, non-destructive way because the brain is a bunch of neurons. And so if you add some more neurons, they grow in and wire up. And this can be an incredibly powerful BCI technology, but it doesn't necessarily help you understand exactly what those cells deep in the brain are doing because you don't necessarily recover the original representations. You can in some ways, but you don't know. Like you're kind of getting a bunch of information mixed together back at your device, or the way that you stimulate it to activate the brain is a little bit different than you would with, say, like a wire. And so that, I think we're going to see a little bit of a divergence between neural engineering and neuroscience, even though they're obviously highly synergistic.
Yeah, in some of the early neuroscience and neuroengineering successes maybe led to things like would you say like the cochlear implant is like a early BCI?
Totally, like absolutely. We include cochlear implants and retinal implants as brain-computer interfaces. The cochlear nerve is part of the brain, and I think a thing that isn't widely appreciated is there's already like over a million people that are walking around with brain implants out there.
Yeah.
There's a lot of cochlear implants, and there's also a lot of deep brain stimulators. So one of the biggest effects in medicine is a Parkinson's patient who you turn on their deep brain stimulator for the first time, and they go from like unable to hold a thing of water to just like steady.
Wow.
And it's not the disease will still degenerate. Like it's not curative, but it is a huge quality of life improvement. It's a huge effect size for a meaningful period of time for many patients. And yeah, I mean, we joke that it's like the kind of the best patient testimonials, or it's like may your product demos be like a newborn having their cochlear implant turned on, or a DBS stimulator turned on for the first time. Like these are effect sizes that you just don't see in medicine, like by and large. Like you do in a couple cases, but this is one of the reasons I really like working with the brain, is because when you have something that really works, the effect size can be huge. We're not talking about like extending a poor quality of life by 2 months in a way that is statistically significant, but not really meaningful to the patient.
Yeah, there's an amazing video. I'll link it in the description of this, where a woman has her cochlear implant enabled for the first time, and she suddenly starts hearing people for the first time, and it's just this amazing experience of expanding her sensory perception, and it's just like this wonderful testament to the good that all these technologies can do. So with that, let's get to the PRIMA device. So first, like what is the problem that you're trying to solve?
So yeah, I mean, there have been cochlear implants for decades, and even though like those are amazing and are widespread, there's still limits. By the way, I think the better cochlear implants will be coming out. Like they're good enough to hear voices, they're not necessarily good enough to take to a concert, and so there's still ways to really expand the applicability. But when you look at the retina, there's nothing like that. There is no like cochlear implant of the retina, and that is a huge unmet medical need. So sensory neural hearing loss is more common than some of these forms of blindness, because the immune system learned a long time ago not to overreact in the eye, because that is like really bad for the organism. But like similar to Alzheimer's, age-related macular degeneration is one of the things that many people are most worried about in getting older. And for there's these what we call outer retinal diseases, where the rods and cones, the photoreceptors, the light-sensitive cells in the back of the eye have died. But the optic nerve is still intact, and the brain knows how to see because they saw most of their life. For these photoreceptor degeneration diseases, there's millions of patients, and there's nothing available. So as a company, we've looked at a range of technologies for restoring vision in through the retina, and we have a state-of-the-art optogenic gene therapy, and then we also have an electrical stimulator. The gene therapy is a little bit further away. That needs to start clinical trials, and will take some time to really develop, but might be capable of really powerful things. And today we have a product called PRIMA, which, I mean, not to undersell it, like the results are amazing. It finished a major clinical trial last summer. It's the first time, to our knowledge, that some of these patients, the trial was in an age-related macular degeneration, that some of these patients have been able to read again. And I actually just saw a video recently of a patient recognizing faces, which was a thing that some of the investigators weren't even sure would work with this generation of device. We have new versions of the PRIMA implant already in development. We actually just got some of the first devices of the next generation back a month ago. And the next step there is to shrink the electrode size so that you can target fewer cells at a time. But for the current version of the device, I mean, there's clips online of patients who cannot see, definitely cannot read natively, filling in crossword puzzles. And that had never really been done before.
And so how does that, so what does a person with macular degeneration see? Like what is their experience, and kind of like what does the form of blindness do? And then how does the device fix that?
So there's 3 layers of cells in the retina that kind of matter. There's the rods and cones that are light sensitive. There's 150 million of those. Those connect to about 100 million bipolar cells. Bipolar because they've got 2 ends. And those then connect to a much smaller number, about 1.5 million retinal ganglion cells. Those are the optic nerve. So the optic nerve cells reach all the way out from the eye deep into the brain. And previously, many groups had really primarily focused on stimulating the optic nerve cells. But the problem is that because the image is already so compressed, you can't just excite them with a camera image. That doesn't produce what we call a form percept in the mind's eye. That just produces these flashes of light that we call phosphenes. And
so that means the documented description is like somebody's visual field, when you stimulate too deep into the optical nerve, they have like these flashes. And so
you get these flashes of light that, like, if you see an artistic representation of it, like if you see a picture of a field of phosphenes, you might see there's like a woman's face, or there's I can see letters from the flicker, from the flashes. But the way that the patients actually perceive this is really different than you seeing the artistic representation of it through your photoreceptors. The brain does not piece phosphenes together into a really coherent whole. Yeah. And so, for instance, 10 years ago, there was a company that got a retinal stimulator to market. They sold 400 of them before it was eventually withdrawn. And they were able to stimulate these fields of phosphenes onto the optic nerve cells. And the best patients could kind of read, in the sense that they'd be like, oh, here's a line, it's connected, that's an A. Here's like a shape, it's bridged this other shape, that's an N. But it wasn't like they were reading off like sentences from a book. And I think it was an empirical finding of this clinical trial that if you stimulate the bipolar cells, so the first way that our device is different is we stimulate that 100 million bipolar cell layer, not the 1.5 million optic nerve cell layer. And this requires us to place our device under the back of the retina instead of on the interior surface, kind of like if you go in through the eye, ironically, the layer that is most forward is not the rods and cones, it is that optic nerve cell layer, which is part of why you have a blind spot.
Like backward.
Yeah, it's backwards. And so the blind spot is the point where the optic nerve dives and exits the eye. So our device sits under the retina, stimulates that first 100 million cell layer, and it's an empirical finding of this trial. It's had not really been done before, that produces a clear form image in the brain. Now, it is black and white. We don't get color with this. Color rolls up through the bipolar cells. We do think that in the next 1 or 2 device generations, we'll probably get at least some red and green. But it acts as essentially an electronic photoreceptor. So the implant is a light-sensitive chip that has all these tiny little pixels on it. And the patient wears glasses that have a camera looking out at the world, although you could get the video feed from anywhere. And then an infrared laser that projects into the back of the eye to strike the implant. And because your eyes are not normally light sensitive in the infrared, you can't see the laser projection. But wherever the light energy falls on the implant, it just absorbs the light, converts that into an electric field that stimulates the bipolar cells, and thereby kind of bypassing the dead rods and cones and getting the visual stimulus back into the visual processing pathway at the first possible opportunity beyond the dead photoreceptors.
Yeah, so basically you're creating a different technical pathway to bypass a layer that's not working, and then activate the layers below that are working, and then generate the image. And so here, I think we didn't describe the experience of a patient with a disease. So you mentioned blind spot. So there's kind of like partial blindness, right? So how does the disease work?
Yeah, so specifically the trial was done in macular degeneration, age-related macular degeneration. And so these patients are not in total darkness. They have some residual peripheral vision. They can use that to walk around and not run into walls. But only the central 6 or 7 degrees of your visual field is actually high acuity color vision. This is the fovea. And your eyes are constantly darting around to figure out where in the scene should I look at next in order to minimize my ongoing uncertainty. And you don't experience, like what you see is not the image that actually falls on the retina. What you actually experience is this world model constructed by the brain, which is actually only relatively weakly updated by the senses. This is one of the reasons that we're so susceptible to things like illusions. And so as the eye is darting around and filling in this world model, that is the thing that you end up perceiving. And so even though these patients, they have some residual peripheral vision, the area of their high acuity color vision is degraded.
To sort of see
they think that they see.
Spot.
Well, no. So actually, patients don't perceive a dark spot because the brain fills it in. Now, if you're really late stage blind, like in dark RP, it's a little different. But so the brain really wants to fill it in because it's looking for information, even if it's not real. And so one of the things that we can do with these patients is you can show like a solid green bar that goes all the way through the visual field, and they'll say that they see a contiguous bar that's green, and then it turns white, and then it turns green again. But they see it as continuous because the brain fills in the area around the scotoma.
And so then, in a lot of these cases, so what are sort of like the impact on people's lives? So certainly, you mentioned they can maybe potentially walk around and so on, but certainly it sounds like they can't read.
They can't recognize faces. They can't order off a menu. They can't
use a computer very well.
Yeah, definitely can't use a computer except to the degree that they can have another assistive device or talk to it or something.
Yeah. And so then with a device, you bypass the layer that's not working. You use a laser mounted onto the glasses to then stimulate those cells. And now they see, what do they see exactly?
Yeah, so this is one of the reasons that the crossword puzzle test is interesting, because we don't, but like in theory, there are ways that you could cheat on other types of object recognition or like these reading tasks. But here, this is a visually guided fine motor task. So most motor control is not visually guided. It's a proprioceptively guided, which is this feedback of your body position. You don't need to look at your hands to catch a baseball or to type. But here, this is a visually guided fine motor task. And by the way, the fact that this works actually says deeper things about how cool this technology is, because if you just prior devices where the electrode array moved with the eye as it moved, or if you put it, say, in cortex or in the thalamus, where as the eye moves around, the electrode mapping is the same, so then the eye movements are no longer meaningful. This breaks a very important connection to motor control. Whereas with PRIMA, this is intact because the eye movements remain meaningful because they move relative to the laser. And so the fact that you can do this visually guided fine motor task is very cool. But these are shapes, and they have to like see the lines of the grid squares. They have to read the letters. They have to fill in the letters between it. And so I think this is really very strong evidence that it like, what does it look like? It looks like vision. Like this is vision, structured form vision. The amount
they're filling crosswords and like reading books.
Yeah.
Wow.
There's
amazing.
Playing card games.
How do the patients feel?
You have to be. The patients are pretty stoked. I have to be clear. This is a clinical trial. You cannot say that this would like work for everybody. It is. We're going through the regulatory review process now. It's not commercially available yet. This is an investigational device. But the results from this trial are like very, very they're great.
Yeah, it's amazing. What are some of the people saying? Like, what are the I don't know if you can talk about that, but. I want to get a sense of like the experience that people have.
I've only spent a limited amount of time directly with the patients, but it's pretty cool to like when I was in France a couple months ago, I went to a rehab session. It's like pretty cool to see them like holding a newspaper and like reading it. And these patients are all pretty elderly. The average age in the trial was I think 81, and that it is a lot to ask an 81-year-old to do anything, especially like a blind 81-year-old to come into a clinic and engage with this clinical trial. And many of them. They really want to do it because this is a very special experience.
So you mentioned France, as far as I know, like the clinical trial started in France, and now you're doing them in the U.S. Can you talk through like what stage is the tech in worldwide?
The main clinical trial was done in 5 countries across Europe. So it was done at 17 sites across France, the Netherlands, Germany, Italy, and the UK. And we're submitted for the CE mark, which is the marketing approval system in Europe and a bunch of other countries. And we are going through the audits now. That seems to be going okay. In addition to the main pivotal trial for that approval, there is a small feasibility study in Europe and a small feasibility study in the US. So there's a handful of patients that have been implanted in the US. We are currently engaged with FDA to talk about the path to market in the US. We also, like I said, have a next generation of the chip already being worked on, that we're starting to think about the human studies for that, which is it's very similar to the current version, but better. And we'll be doing a clinical trial for that, both in the US as well as Australia and some other countries.
That's amazing. And do you think this device can then be used for a range of other diseases, or is this like very specific to this one like family of problems?
Well, the family of problem are photoreceptor loss diseases.
Sounds pretty general.
Yeah, and so there's a bunch of different reasons people go blind. I mean, one of the most common are things like refractive errors, like cataracts, that are easy to fix with surgery, done all the time. It's one of the world's most common surgeries. Then there's glaucoma, which is loss of the high eye pressure, which can lead to loss of the optic nerve, or potentially other reasons why you would lose the optic nerve, say trauma. If you've lost the connection to the brain, this does not work for that. But for a relatively broad range of diseases, I mean, one of the things that's nice about our approach, both the gene therapy as well as PRIMA, is that it doesn't really matter why the photoreceptors died, as long as you can stimulate the cells past them. I think this is when we would talk about neurotech, I think some people would say, well, like, this is ophthalmology. We've been doing ophthalmology for decades. Obviously people have been trying to restore vision for a long time. There's all kinds of drugs, there's gene therapies, there's a bunch of devices, like what's different? And neurotech is really, there is a different lens on the world that you can think about many of these things more in engineering terms than you could have before. And it's different than the other gene therapies and drugs that are out there, because we don't necessarily care why the photoreceptors died. We just care that we can think in terms of the information and the representation that we need to inject into the brain in order for you to experience the visual information and get the visual experience. And so, beyond macular degeneration, we're also thinking about retinitis pigmentosa, Stargardt's disease, which is some like macular degeneration that affects young people, diabetic retinopathy. There's a bunch of different potential indications that we'll be needing to do separate studies on.
Yeah. How many people does that represent, like globally?
Macular degeneration is one of the largest of those. I mean, glaucoma is big, but I'd say it's in the millions of people.
So if you succeed, if you get this device to market, if it works out, if it's successful, you could literally help millions of people around the world restore their vision. That's awesome.
That's the idea.
That's great. That's super awesome. What is holding? I guess you have to go through the trials, and that takes some amount of time. Can you maybe walk through what that looks like? Because of course, every day or year that passes without this kind of thing is there's kind of significant loss there globally, right? Of a day or a year that people don't have these things.
I mean, this is there's some patients, I mean, medicine can move very slowly, and clinical research is a very deliberate process. And I mean, some of the delays, to be totally honest, there are patients, it's the risk benefits for these patients, it's if it takes another 2 or 3 years, they're not going to be there. They're not going to get it. And so medical device R&D and translation is a very slow and deliberate process. The PRIMA technology was originally invented at Stanford by a professor there named Daniel Planker, and it's been in development for, I think, a decade now. And so that's the time scale that it takes to bring something like this to market. Now, I think that, like I mentioned, that we're doing a trial in Australia. So the first version of basically anything is always pretty limited. The first iPhone was pretty cool. I mean, that was a huge advance. But I mean, the first iPod was a spinning, they put it together in 6 months, and that in itself, if you look back now, to that versus what we have now, the really cool stuff is in versions 4, 5, 6 and beyond. And so I think we now, in PRIMA, we have this existence proof that you can create a form image in the mind, and that this basic approach works, but there's a bunch of ways to make it better. And so we're going to, every 2 years or so, to be coming out with a new version to begin to realize the potential of the technology through these refinements, and being able to do that and kind of quickly and easily to get feedback from human subjects and feed this back into technology development is really important. We only work in sophisticated, modern, developed health systems. We're not going off the reservation to go do this somewhere sketchy, but wherever. But we're always interested in moving as fast as we can.
Yeah, and I mean, there are probably some countries and jurisdictions that are starting to think about leaning forward and going faster on this. I've spoken to people in UAE, for example, that want to kind improve their create pathways for neurotech to advance there. Is there like what sort of like advice would you have for government folks globally to think about like improving their systems?
Yeah, I mean, I don't know that I would answer that specific to neurotech necessarily. I think that there's kind of on multiple levels opportunity for clinical trial reform. Now, healthcare is this, to a great degree, really represents a market failure. It's something that everybody has to deal with. The willingness to pay is basically infinite. And then it requires big investments in very specialized labor and a lot of very specialized infrastructure. So it just kind of on many levels leads to these big economic distortions that need to be corrected somehow. And I mean, I think one of the most valuable thing that any regulatory body can do is just engage actively, because if it takes if it takes 2 months to figure out if something is possible versus 8 months, like even if the conclusion is the same, like whatever the rules are, the rules are fine. But being able to get feedback in 2 weeks versus 2 months versus 6 months, this has a really profound impact on the types of entities that can play in this. Like if it takes you a year to get just like even feedback on a clinical trial protocol, then the only people that can do this are like super highly funded giant companies that think in decades. And it's just too hard to venture fund a lot of this. And even if the return could be there, bridging through that is very challenging. And so I think anything that we can do to compress these timelines is going to really encourage innovation. Yeah. And there are biological time constants that can't be avoided. Like at some point, you need to just follow some number of patients for 2 years or 3 years and get the safety follow-ups to make sure that they're like certainly before you go to more patients. But just the paperwork, we should like if you send a letter saying, hey, we've interpreted this rule this way, and then there's like a 3-month delay that
yeah, exactly. Like the biology can
hard
take
to innovate.
The time that the biology needs to take. And for safety, you have to allow the trial to pass for a certain amount of time. But if there are delays that are in paperwork or things like that, that seems like a huge problem. You mentioned upgrading the device over time. Like how would people then like when the new upgrade rolls out, like then get another surgery and like just replace the device, or like what does that path look like?
Potentially, yeah. I mean, one of the things that's nice about PRIMA is it might be upgradable. We've never done this in a human, but there's animal evidence that this is possible, and so it's a tiny little fully wireless chip. Like PRIMA being powered by the light that is used to activate it is this that's a really cool trick.
It's like a great innovation.
Yeah, there's no cable, there's no battery. Like their prior implants had like a cable coming out of the eyeball to like a titanium box. Like you can get rid of all that. You just have this tiny little silicon fleck. And we think that it'll be possible to upgrade it. Now in practice, probably in the first generation or two, that won't happen that often. And then as you start going to younger patients who are less disabled for a more powerful implant, then you'll, I think, start to see that more. Certainly, if you're talking about like a 25 or 30-year-old Stargardt patient, they're going to expect to get a handful of upgrades over their life until we can get towards native acuity color vision.
Right now, the idea of having one surgery sounds intense, like multiple sounds even potentially scarier. How do we kind of enable this to be like super easy and routine? And
it's a super simple, like 1 hour outpatient surgery. So this can be done under local anesthesia. I mean, it is often done under general anesthesia, but that's like as much for just like nerves and for like, you can't change your mind halfway through the surgery. Yeah. But it can be done. You just make some injections next to the eye. It goes dark and numb for a few hours. They come in through the front of the eye. They leave the chip in the back. I remember when I got into this field, like almost 20 years ago now, it takes a little while to acclimate to photos of surgery. And I think everybody has this experience of going from like, I don't really want to watch the videos of surgery to being like, oh, check out that vasculature. That's like super defined. And like you can like see this part of the brain. And then when I moved to start working on the retina, it was a whole different adjustment to start looking at videos of like eye surgeries. Yeah. But you acclimate to it, and it's just like, and then you're like, oh yeah, there's like, you can see that like you can see that marker, and it's like, oh, you can see where the implant was placed relative to this blood vessel. And it's really not a big deal. The patients tolerate it well.
And certainly like the ability to recover a sentence is probably a lot more of a difficult surgery and recovery process. It sounds like it.
Yeah, I mean, and this really is not a difficult surgery. I mean, like a brain surgery where you're drilling a hole in the skull and tunneling into the brain, that is like way more intense than this outpatient, like leave a little wireless chip in the back of the eye. Because the eye, you don't have to go through any bone to get to the eye. The eye is soft tissue. And so it's surgically easy to access. You can look at it by like looking in through the eye because the eye is clear. And so on many levels, this is, I think, a much easier surgery than some of the other things out there.
That's a great segue. So let's talk about the Biohybrid. So you mentioned it a little bit earlier, but let's maybe start general and then dive in. So how do brain-computer interfaces work? I mean, we've definitely been talking about maybe special purpose or special case BCIs, but kind of what's like the general vision of the BCI field? Like meaning being able to like do read and write into the brain. How does that what's the possibility space here?
Yeah, I mean, I don't know that the BCI field has like a general theory of the vision of BCIs. I think this is part of this is like one of the issues right now, where there's some very classic BCI applications, like extracting motor representations to control a cursor or a robotic arm or a keyboard, or more recently speech decoding, extracting speech from the brain from ALS patients. Or I actually saw some data recently where some nonverbal autistic people might have speech representations that could be decodable with a speech prosthesis. That hasn't actually been done, but there's evidence that could be possible. And that's the type of, I'd say, like neuroscience that isn't new, but the devices are getting better. Now, does a better motor decoder is that the big prize at the end of, I think, where a lot of people are imagining right now? Like, I don't know. There's kind of vague gestures to maybe you could improve memory, or maybe you could improve reasoning, or maybe you could have some other capability. I think that is kind of harder to reason about right now. I think that's not really clear what that would mean. But then at the other end, I think when I think about like something like Biohybrid, where you're thinking, really, can you add whole new brain areas, or can you add almost a new hemisphere to the brain? This takes you into like even like kind of more out there sounding territory, where can you, in some like very profound sense, like redraw the border around your brain? Can you add new things to that system? So then you go from thinking about just exchanging information with the brain, like extracting motor information or writing sensory information, to kind of adding a whole new part of the brain it didn't have before.
Yeah, I mean, right now already, so many people are deeply integrated with their phone and like their personal devices. Like these are kind of part of them in a way, but they just haven't crossed the barrier, and like you still have to go through like the eyes and your thumbs to type or whatever. But like if you open the bottleneck and you then enable you to like think with your computer, like what does that look like? What could be possible here?
So there's a lot that I'd say is like debated in the field right now. So there's some potential limits. So human language is about 40 bits per second. There's different interpretations of that, but if you just think about the number of bits of information that are kind of reduced, like you've got a space of phonemes, like the words that can get put together. You choose one from that some number of times per second. Some human languages are spoken more quickly and convey less information per token. Some are spoken more slowly and have more information per token, but in all cases, it's about 40 bits per second. Now, there's also some evidence that there's this deeper cognitive bottleneck in the brain at about 10 bits per second for like reasoning and experience. So if you put someone with a photographic memory on a helicopter flight over Manhattan, then for an hour, and then ask them to draw what they saw, and then you look at the details that they got, averaged over the hour, it's about 10 bits per second. Or there's just kind of many different ways to triangulate this number. And so that leads people to think that there's this like deep bottleneck, which is co-evolved with all the different brain areas, that kind of serializes thought at about 10 bits per second in terms of what you're able to remember and act on. And so in that sense, just like opening up some bottleneck may not necessarily help you. Like you feel like you could speak faster, you feel like you have all these ideas, but the reality is that until you serialize these in this way, they aren't actually formed and you can't actually use it. Now, on the other hand, even at 10 bits per second or at 40 bits per second, there are faculties that you don't have or skills that you don't have. This is kind of like the I know Kung Fu example.
Yeah.
And so that doesn't necessarily cheat that limit. Like you could, those bottlenecks could still exist, but at those rates, the brain could have the ability to transform information in a different way than it would have otherwise had.
So the I know Kung Fu moment from the Matrix, where Neo just like downloads this capability and is now suddenly able to control his body. That probably requires training the motor.
Yeah, we don't know how to do that right now.
Yeah, that seems like
totally.
surprisingly harder than like, let me remember Wikipedia, or I don't know, let me look at my message inbox with my brain. Like, what are some of these like other things that seem more likely?
You can almost think of it as like a UI UX problem. Like, what is the UI UX of a BCI that was what you want for accessing something like Wikipedia? Because like the iPhone is a crazy technology in multiple levels. Like it is, if you want to talk about addiction, like many people, if they're physically away from their phone for more than a couple of minutes, that they get noticeably anxious. Like that is a crazy technology for what that does to our brains and how it rewires it. But
could it just be like more like less kind of like dopamine addiction and more kind of like a sense of self evolving into it, where like
kind of, yeah. And so like the thing I was gonna say is like you have already
I'm addicted to walking with my legs, right?
To Wikipedia, but when people rely on phones more, their memory degrades. Similarly, people that use GPSs to drive have worse spatial capabilities than those who don't. And so the brain is definitely offloading. There's something that's not being exercised that it's realized it can offload, that it can draw upon. And so that is definitely already happening. But if you wanted to integrate this directly into the brain somehow, it's like, how should that be exposed? Like, should this be exposed like internal monologue? Not everybody has internal monologue. How do you cue this thing? Do you want to just be able to like have a thought, be like, oh, I wonder like what is the GDP of like Micronesia or whatever? And then you just like, how should that be delivered to you?
When you think of kind of like, I don't know, maybe like not a super long-term future, but like maybe like a short near-term, I suppose that we get something like the Biohybrid and we're able to expand the connectivity. Yeah, what are like the UX sort of capabilities that would suddenly like be unlocked?
Well, I mean, to some degree, this gets at like, what is your unannounced research? Because I think there's
whatever
some really cool stuff that
whatever you want to tease the world
forward to publishing. Yeah. I think this idea of like adding new brain areas entirely is underexplored. And you have like clinical needs for this in cases like stroke, where a patient might have lost some part of their brain that underlies, say, speech or some part of reasoning or some part of memory. And if you can restore that capability to them, then that is a really valuable medical need, and also hints at potentially other types of expansion of capability.
And so concretely, this would be like adding a chip into your brain that would then carry along some amount of those capabilities, or would like connect to the phone or other devices.
Yeah, I mean, you could do it potentially either way. So with Biohybrid, there would be a device that has these cells that the cells grow in, they form new bidirectional connections into the brain. And then those cells, we think of them as they kind of join the local cortical representations. So for example, we know that if you have a Biohybrid implant in a mouse, and then you have a mouse in a treadmill, we can recover how fast the mouse is running through these cells. So we know that the dendrites of the Biohybrid graft cells have grown into the brain and formed connections that join these like paw kinematic representations. And then also, if you have an animal in an environment, it's making a decision, you can give it information that it can use to make that decision through a Biohybrid engraftment. So we know we're getting these axonal synapses. And so when these things grow into the brain, they form connections with the neighboring tissue, and these things. Well, the Biohybrid engraftments are pretty cool. They grow pretty deeply into the brain. I mean, you see connections all the way down to subcortical structures like the thalamus, and so it's totally possible to imagine that you could add like a new corticothalamic loop that instead of going through a native part of cortex kind of ends up in your device, that then you could process either locally or you could send over a radio to some other larger model running elsewhere.
And that would start hooking in entire subunits of computation into your brain. Like it seems like the brain could start calling out to these kind of subunits to do complicated tasks.
Yeah, I mean, exactly. Like, can you add new pre-trained representations to cortex that you could draw upon is like a really interesting idea. There's a huge amount of basic neuroscience to do here.
So from a computer science perspective, this looks like opening up the whole operating system and programming application structure, and then replacing interfaces in between with like calling out to APIs in the world or like in your device, and like filling in larger amounts of information processing or computation to then be able to like access it as like part of your intuition or your thinking or.
Yeah, I mean, you kind of have to think of the brain as an information processing organ, and it's really about these informational flows. And I kind of, you can have this mental model of the brain as just this like thing that is full of these abstract objects called representations. So there's a representation of my hand that the state corresponds to whatever the motor control is and whatever the current proprioceptive state is. And you want to be able to access these so that you can decode them or recover them or drive them and create them. But these things, like this field is really young and moving pretty fast. And there's a lot of basic research that we'll need to do to really kind of understand all of how to use it and all of the implications. And we do a lot of that internally, but we also try to collaborate with outside academics and get tools into their hands so that, I mean, we're a small part of a global community, and there's a very deep well of neuroscience and biology to do with these types of devices over the coming 10 plus years.
Let's go through maybe an explanation of the Biohybrid again, like walk through the description.
The central idea is that instead of placing wires or like optical fibers or anything like that into the brain, we can make a device that we can load but like in a dish. Like before you put this into a patient, you just like have it in a dish, and you can seed this with living cells that will turn into neurons in a very predictable way. And there's a bunch of different ways that you could do this. We have a bunch of different probe designs. But the key is that you have these cells growing really directly on the electrodes, whether these are like actual electrodes or things like LEDs or imaging pixels. And
how do you talk to the cells?
So typically so neurons store information in a voltage across their membrane. So you can think of a cell as like a fat bubble full of saline and a bunch of other molecules. And so neurons they're a type of a cell called an excitable cell, which have these proteins that go across the cell membrane that allow them to pump charged particles around, basically, so they can control their membrane potential to store information, do computation. And this is detectable with an electrode. And so you can just have what we call a capacitive electrode because of how the physics of the device works. And so if you've got a neuron next to your electrode, if the neuron pumps ions around, you can detect this with your electrode. So you can record the cell state with a conventional electrode.
Yeah, it's basically reading the state of a single neuron.
Of a single neuron, yeah. And you can also inject charge through an electrode in order to depolarize a cell. So what you're doing there is you're kind of increasing the concentration of a charged particle next to the cell, which has the effect of kind of moving because a voltage is a differential measurement. If you've got, say, like a 120 millivolt potential across the membrane of the cell, that you can change by either pumping ions across the cell membrane or just like changing the external concentration, which will have the effect of implicitly changing the membrane potential. So you can do that. That's the most common approach. We call it microstimulation. We mostly don't do that because you can't stimulate and record at the same time. And also there's some other biological effects of that type of stimulation that aren't ideal. So what we do is we express a special type of protein in these cells that make them light sensitive in a particular way. So it's a light gated ion channel. So it's like one of those like holes in the cell membrane that allow them to move ions around, except this one is open or closed depending on if there's light of a specific color that is being shined on it. And so in addition to our electrodes, we also have micro LEDs in the device, so that if we want to fire a cell, you turn on the micro LED next to that cell, which will cause it to open the channel and then that cell to fire.
So you have like a tiny LED right next to the cell. It's shooting photons into the cell that is activating.
That opens the channel, it causes it to fire. Yeah, exactly.
Yeah, wow. And then, and so that's like the optogenetic opsin, right? Like, can maybe walk through like why that was such like a breakthrough innovation?
So those proteins are called opsins, and so this is a field called optogenetics. They were originally discovered, I want to say almost like about 20 years ago, originally in some algae. And so optogenetics is a very widely used thing in neuroscience now because it allows you to get to kind of causally influence these neural networks. So it's one thing just to record neural activity, but if you want to say, well, what happens if I drive this cell or this population of cells in a particular way, optogenetics is very powerful for that. And so we use optogenetics in a range of different things. We use it all over the place as a research tool, but then in our products, we use it in two places. One, we express our opsins in our biohybrid cells that make them light sensitive. And this, like, opsins are a major area of research for us. We have an internal protein engineering group that has developed the world's most sensitive opsins and are continuing to improve their properties in a bunch of different ways. Having very sensitive, meaning it takes a small amount of light to open or close them, is important, because if you want to have more channels and you want to have more cells, then if it takes less light to activate a cell, then you can have more LEDs in the same amount of power consumption and as importantly, in the same amount of heat generation. Because one of the things that really limits what you can do with an implant is when you use it, how hot does it get, which is a function of how power efficient you are. And so by having opsins that are very, very sensitive, that take much less light, you can have way more LEDs, because each LED is much dimmer. And so you don't run into these thermal limits. We also use our opsins in the retina for next generation retinal therapy. And it's just, I think we have this intuition that nature is a great engineer, and like when nature has a problem to solve, it makes a protein, and we should be inspired by this. And this is something that's really been enabled recently by the amino acid language models. I mean, this is really, I'd say, AI-driven innovation. I think we don't like talk that much about, like, we don't dress ourselves up as like, oh, we're an AI company and like it's AI powered and you should invest because of AI. But that's a concrete example of how we use modern AI technologies like transformers for practical applications that can be really valuable.
Yeah, it's awesome. Without going super deep into the AI rabbit hole, how much do you feel like the latest models have accelerated your R&D?
So in a couple places, they've been really impactful. So for example, protein engineering is probably the single biggest impact. The other big place that we've used a lot of AI techniques are actually in like regulatory documentation. And we have to generate thousands and thousands of pages of regulatory documentation. And then we need to check that all of what we've done is compliant with like hundreds of standards that have like super detailed criteria. And so that's the type of thing that just as an automation tool can be useful. Everything we do is always like signed by a human. Everything's read by a human, but as a productivity lever, has been pretty useful.
Yeah, generating like thousands of drafts of things and so on before you like actually settle on something. And it's probably happening on the other side. Yeah. Like all of your applications and so on are probably being read by LLMs and like distilled and summarized and so on before whatever response gets back to you.
I hope so. I mean, they should be. That would definitely, I mean, anything that allows us to get responses faster would be great. And I mean, clearly these need to be reviewed by humans and signed by humans, but as a productivity tool, AI has a lot of potential.
Yeah. Okay, so then you have these cells that you can read from electrically and you can write to optogenetically. You can drive a single cell. The cell is like living on a well in this whole sheet of silicon. And that's kind of like, you'd like fab a chip with the LED to be able to like drive it. And I guess you have like a whole bunch of these cells in a grid. And like, how big do these grids get? Like how many?
Yeah, so we do have designs, which I think you've seen, where there are like wells that individual cells are in. We do some of that. We also have other designs. The microenvironment of like a surface that these cells, it's a pretty complicated co-culture of a couple different types of cells that are happy to survive kind of at this silicon interface. That is like super detailed, and a lot goes into that, making this microenvironment that these cells want to survive and thrive in. And we've learned a lot over the last few years. Probably the deepest area of IP on the biohybrid technology for us is actually the cells themselves, which we've heavily edited to make them compatible with patients' immune systems and have things like these opsin proteins, but also have a bunch of other safety mechanisms built in. But then second to that is a lot of what we've learned about building microenvironments that these cells will survive in, including through the implantation procedure, which is like a pretty harsh, like hypoxic, glycemic, other types of shock happening. These like typically, if you just take a bunch of cells and inject them into the brain, 99% of them die. And so there's fairly deep technology around making them survive and thrive there.
So you then have there's like how big did the grids get, like roughly? How many like cells?
Well, the biggest, I mean, so we routinely engraft 1 million cells. Our standard probe right now is 4 millimeters by 4 millimeters. Cells are really small. Like there's plenty of room at the bottom.
Yeah.
The limit on the size of a specific of like that end of the probe is just the brain is curved, and you kind of want something that has more small little islands rather than like a big chip that you're going to try and like squish on the surface of the brain. But within a 4x4 millimeter probe active area, you can easily fit 1 million cells.
Wow, that's awesome. So that means, and is that each of those?
Yeah.
I guess.
To be clear, there's that device right now does not have 1 million electrodes.
Okay.
It's a way smaller number of electrodes than that, but it should be possible to get. And again, this is really limited primarily by it's limited by like power, thermals, and also our willingness to pay very large amounts of money on nice chip processes. And so you can kind of prototype this on some older chip nodes for hundreds of thousands to $1 million or so dollars, and then start just shrinking it, and then you quickly find yourself spending $10+ million at a time on a chip tape out. And I think we'll get there within the next few years, and that allows like a very straightforward scaling. Like I think it is possible to get to a place where you're talking about millions of channels with billions of cells, but like the one step at a time. We've shown like we definitely get dendritic connections, we definitely get axonal connections. We're translating this up to larger animals, and if we're working methodically.
Yeah, and the dendritic and axonal connections means when you implant the device, you are connecting into like upstream of loops and downstream of loops, right? Like you're making.
Yeah, it just means that your cells are getting inputs and outputs. Yeah. They're exchanging information bidirectionally with the brain.
Yeah. So then so you take this grid of cells, you implant it in the brain. The cells grow their axons into the brain and wire. You were mentioning they go super deep.
Yeah. Well, if you think about like a motor decoder, so this is usually implanted in this thing called the precentral gyrus. So there's this primary motor cortex is the strip at the very top of the brain, but from there to a muscle is like 2 synapses. Like the axons from the cells in primary motor cortex go all the way down the spine to the vertebrae that's at the level of wherever that connection is, and there's a synapse, and then it goes out to the muscle. And so neurons can be quite spatially extended. And I don't know if this is...
It's pretty amazing.
So neurons are used to being super long. They do this all the time.
Yeah. What sort of process drives this wiring? Do they just kind of like automatically do this?
This is the developmental program. I mean, they do this... I don't want to say totally on their own because again, the stem cell biology here is pretty cool. But
neurons want to wire and learn.
But yeah, I mean, this is what neurons do. Like when we engraft these things, you see them wire up like very broadly, and then they get pruned, and then there's more active things that happen. But the neurons want to learn.
Yeah, and so as soon as you connect it and so on, what have you sort of like detected from the types of systems that they wire into? Like what kind of experiments have you done?
Yeah, I mean, so like I said, the things that we've published, that we kind of have announced so far are like very focused, like enabling studies on, you want to show like the inputs to these cells are growing into the brain and forming functional connections, and you can recover information from the brain.
It sounds like this. So maybe even before the more sci-fi use cases of being able to kind of interact with a computer and integrate and so on, it sounds like this could even help with a bunch of the motor problems, like being able to wire parts of your brain to, I don't know, across like a severed spinal cord or something like that.
Yeah, potentially. There's so one of the labs that was into, I mean, they didn't call it Biohybrid at the time, but it's really the same idea of using they called it living electrodes. There's a guy at Penn, Casey Cullen, who's been into this idea for a long time. And yeah, I mean, one of his ideas was, can you get axons to grow along these channels to build things like jumper cables in the spinal cord to bypass a break? Yeah. And so like the spinal cord jumper cables idea is an old one that people have made progress on. And there's some animal models that have really cool results. So that's not something that we're doing like in that embodiment specifically, but others are.
If they're wiring this way, couldn't you like start creating like additional senses? Like this goes to your like new brain area sort of thing, but could you like add a sense?
I mean, that's certainly more speculative, but that's exactly the type of thing that I like am excited about. To do this, you need a theory about like what are senses, like where do they come from? Like why do you see and hear and feel and not other stuff, which I have thoughts on. But getting to elaborate that and show some of these things, I mean, I think that it's been bottlenecked on probes and electronics. Like we just haven't been able to get these bidirectional connections into the brain at a scale that allows you to really do this in a way to seriously ask these questions about like what would a novel sense be? I mean, I think that we're going to be getting into the stuff within the next decade.
Yeah. And what is the path? What does the science and engineering and then eventually product building look like there? Like sounds like there's a whole bunch of fundamental science to do right now with these new device to figure out, what you integrate into and so on. You've already done an enormous amount of engineering of figuring out the device and how to make it work and how to increase the channel counts and so on. Seems like there's probably a whole bunch of safety and health oriented testing to do what does that look like? What does that track?
Yeah. I mean,
how many years is that?
In some sense, you can kind of have a debate about whether biohybrid is more or less invasive than other options, because in some sense it's less invasive. Like, it does no damage. It's perfectly biocompatible. The brain is happy to accept these things. On the other hand, you've got a biological cell. You have a cell therapy, which is engrafted, which is forming these it's like a really deep, you can't really easily remove that unless you chemically kind of cause these cells to die. And it has like a bunch of structural advantages. They could last for decades. You can have massive bandwidth. It's like they really enable things that might not be possible any other way. On the other hand, you have totally novel risks to think about. And so there's actually a long history of people getting cell transplants into the brain. And this was one of the things that made us think that this could work, because like if you go on PubMed, like the scientific, the medical literature database run by the U.S. government, and you search for like Parkinson's cell transplant or like Alzheimer's cell transplant, there's actually a lot of doctors out there who've had like a couple patients who you're like, what this patient needs? A stem cell injection to the spine, and or like a cell engraftment to the basal ganglia, and those historically have not really helped the diseases, but they did teach us a couple of things. One, the cells tend to survive and functionally integrate. They'll last decades and nothing bad happens. And so there's actually a pretty large body of like supporting evidence that even in some cases stem cells that I don't think you would have necessarily like wanted to inject into the brain that way turn out to really be pretty safe and pretty well tolerated. And so we think that will turn out to be fine. But it's going to be systematic from whatever you can do in a dish, you do in a dish. Whatever you can do in mice, you do in mice. Whatever you can do in a rabbit, you will. And then you start working up to, you have to do some monkey studies, then you go to humans. And certainly anything in humans is much slower and much more methodical than what you do in animal research. But at some point there'll be some first patients. And I think that it'll probably most likely be stroke. There's a population of stroke patients that I think are probably likely to be the first biohybrid recipients. It definitely won't be next year, but I think it'll be way less than 5 years from now.
And so from there, what's the path to, like, how long is the trials landscape for something like this?
It usually takes at least 3 to 4 years to get through a clinical trial for something like this. Because you'll spend a year kind of getting set up, you'll write your protocol, you'll get IRB approval, you'll get all your documentation. That takes like at least a year. And then you'll enroll your participants. That can take a while. And then you'll have to follow them for at least 12 months. Like, there's no way that the FDA is not even going to look at your data for less than 12 months. And they'll probably want 2 and 3 year follow-ups, but you can kind of do that as you go. And so if you've got a 2-year endpoint and they really want to see a 3rd-year follow-up, then you have like a year of setup. You have a year where you're kind of implanting everybody, and then people will start hitting the 12-month check and 24-month checkpoints at some rolling window after that. Once you've got a suitable number of patients out to 2 years, that's probably enough to start thinking about submitting a larger filing to the FDA. And then while you're going through that process and they're reviewing it, you'll start to get your 36-month data in, and they'll look at that as it comes in. And then after that, you can imagine like another year to kind of get an approval and get on market. So that's at least a 4 or so year process.
Plus the sub 5 years that you mentioned now, that could be, like within 10 years, this might.
Yeah, it could be on market. And but at the same time, we're going to learn a lot. And going to market is one thing. And the way we actually architected the company allows some of that to be a little more backloaded. So our retinal prosthesis, specific like PRIMA in particular, we hope to be on market with that next summer. That could get delayed. We are going through the regulatory process now. We don't have the approval yet, but we think it's pretty likely that we'll get approved in the next year. And that alone is a big enough product that it can finance a lot of the rest of the stuff that we want to do. So the company, like we're thinking about how do we get profitable, not just like, oh, we want to raise another $5 billion of venture or something over the next 5 years. And so,
Wait, if you get profitable, what's the timeline? It seems like one of the fastest biomed oriented companies to become profitable.
well, we can say that when we've done it. Like, let me get there first.
Like if you can get there.
But if you get there, exactly. But I mean, I think, I don't know, I running a startup is
there a website tracking these? Like, I want to make that.
I'm sure. I mean, it's like annoying to look at the software versions of this where it's like they're like going to
like 100 million ARR in a few
8
weeks.
months or something. Yeah, it's like, well, you can't do that. But but I don't know. It's like the startups.
Maybe have a team doing that, and then that funds the rest of the program.
Yeah, well, we're grateful for PL support and investment over the years. But I mean, the goal, like the visual prosthesis is really a big enough business. If we don't mess that up, that can be a multi-billion-dollar a year source of cash, fully developed. And that buys us a couple of things. One, it buys you time to go through the full regulatory process for this, like the world's most complex combination cell therapy device kind of ever made. And it allows us to fund some like the parallel research along the way that I think will really prove out some of the big concepts, like the missing theory, prove that some of these really next generation type applications are possible in animal models in small numbers of humans, separate from like a market approval study, because you can have these smaller studies where you'll implant a couple patients, like 3, 5, 7 patients, learn something very targeted, hopefully help them with some disease, but at least get a kind of prove out core elements that are missing. That is very different than like a market approval study where you've got like one thing that you're going to do very little to tweak, and you implant 50 or 60 patients and you follow them for 3 years. Like those are very different types of things. And so I think that like our plan, like the secret master plan here is bring a breakthrough retinal prosthesis to market, use the revenue from that to fund the development of the Biohybrid core technology, use this to prove out kind of some really, I think, big prizes of emerging neurotech, and then eventually, of course, translate this to market. And I think we have this vision of how we think the world is likely to look in the early 2030s. I think 2030 will probably still look a lot like today. I mean, this is also AI and other things happening. But I think 2035 is likely to look quite a bit different than we might be imagining right now.
Yeah, at some point we should do that conversation of like, what does 2030 look like, and what do we think 2035 is going to look like? Yeah. Stay tuned. Cool. So first of all, that's super exciting. Like we're talking about like if that happens within 10 years of now having very high bandwidth BCIs that you could then start using to drive computers interacting with AI, interacting with people, and so on.
Yeah, I mean, your entire experience of reality is rooted in the brain. And so this is also like, it's important to be very sensitive, because this is like your sense of identity, your sense of self. Like people do not want you to mess with this. Like, and I think we hear that, we're receptive to this. Like we want to make sure the goal here.
And at the same time, people want to be able to experiment and explore and improve, like change their own sense of self and so on, right? So just as much as a set of people want to be able to have what they had in the past, restored, if like they have some disease or some damage or an accident or something like that, and they have their sense of self and mobility and so on be able to be restored. Just like that, there's a population where a set of people want to be able to enhance their capability set. Like they want to be able to improve their senses, be able to like see in a different part of the color spectrum, or being able to like add additional senses, or be able to like interact with their phones or computers in deeper ways. Like what does that look like? And like I don't know, what are the kinds of things that you want to be able to
some of these things will be possible. I think there'll also be cultural like discussions that happen along the way. I think,
and on that, I think OpenAI is probably doesn't get enough credit for shipping ChatGPT and having the big AI conversation in public. Like I think there was a lot of concerns. A lot of the AI community was very divided on should you deploy, should you not deploy, should you have like the conversation in public or not. But from my perspective, I was always very pro having these kinds of significant changes that are possible appearing early while you can still like figure out what they're going to look like in the long term, and kind of enabling the broader groups around the world to come to terms with these kinds of potential futures, right?
Yeah.
And chart a path and figure it out together. Like, where should we go?
AI is a very cool technology. Like, it is clearly going to enable us to do things that were never possible before. It is definitely like increasing the pace of innovation of society. But also, I mean, you can have some concern that it is kind of a dehumanizing technology, that it could, I mean, there's some, like, I mean, very famously concerned that it could replace humans and have other existential concerns. But it's kind of an inherently dual use technology. Like, it is possible that just intelligence is itself dual use. Any differentiated understanding of the universe is dual use. Like, for example, like if you've got a better understanding of physics than anybody else, you can build nuclear weapons. Or if a civilization has calculus and one doesn't, then like one is going to have an advantage. And so kind of any differentiated understanding of reality is dual use, and AI is kind of, I think, the ultimate embodiment of that. Now, on the other hand, BCI is in some ways like a more intrinsically benign technology, because just because somebody has a BCI does not necessarily mean that it's like there's a different category of concern you might have versus like if you heard like somebody has an AGI and it's they're the only one with it, I think a lot of people are like,
Yeah.
But if it's like, oh, there's one person with a BCI, that's not dangerous in the same category. And so I see this type of these neural engineering.
Maybe. I mean, it depends on,
Depends on what you do with it. But in itself, intrinsically, it is like without some other thing happening, it's kind of like, I think the promise of this technology is to increase and empower like human agency. It is like a fundamentally human technology. And I think if you look at like the endeavor of lowercase s science, like what is the purpose of this? Like we're trying to understand reality, or trying to understand the world in order to improve the human condition. We use the knowledge that we get through research in order to improve our lives. Like back in the Middle Ages, playing in the forest was dangerous. Like a kid got a scratch on the wrong tree and then it would get infected and they would suddenly die. And there's like nothing you could do about this. And there was just this constant jeopardy that life was under, and this was just the human condition. And now
it's astonishing, by the way. We do not today at all have an appreciation for how dangerous life was in the past. And
But even so, like in the same way, like people don't think like, oh, like maybe I have an undetected cancer right now. Yeah. Like that is in the back of the minds of many people. And so it has changed and it's certainly gotten better, but the fundamental human condition is still there in that way. And so kind of the endeavor of science is to improve the human condition. I see neural engineering as like a very powerful, one of like the very deep nodes on the tech tree that begins to more dramatically allow you to maximize human agency and improve these things in kind of multiple different ways.
Yeah. How much do you see this is an imperative for de-risking AI, right? So from my perspective, there are massive amounts of AI risks around capability explosion and generating a new agentic species, whether they might develop a degree and level of agency that is very difficult to prove anything about or to have certainty over. And so it can quickly become, in some sides or like traditional sci-fi being like deep competition with humanity, or in some more, in some of the ways that have been talked about in the last few years, not even in like harsh competition, just in this weird taking over of control of the world and kind of eroding human agency or control of the future. Neurotech has seemed to me over the last 5-10 years as one of the major avenues that we have to be able to stay ahead, or if not ahead, even at least stay competitive in the long term, and to enable humanity to have a path into the future. Like, how much do you think about that? How much of that is like, I don't know, motivating? Curious.
Yeah, I mean, I think there's a real risk that AI does to us what we did to the chimpanzee. Like 200,000 years ago, humanity was an undifferentiated primate on the African savanna, and now our closest living relatives live in glass boxes so they don't go extinct. Like, what was different? Like our intelligence. Like we were more adaptable and we could adapt and we could collaborate better as a group. And I think that's a real thing. Now, the only constant is change. Like I think there's some people think like, oh, this started like in the 90s with the internet, or maybe like the 2000s with the smartphone. This process I mean, other than has been like the story of human civilization, really started in the mid 1800s. Like I think this really started with the Industrial Revolution, and there was a generation that went from like a horse and buggy to seeing a man land on the moon in routine jet travel. And I remember maybe 10 years ago, we used to joke like around Silicon Valley, like, oh, we wanted flying cars and we got 180 characters. Like, what went wrong? And like, will we ever see a situation where like that going from like having a horse to like the 747, like, will we ever see something like that again?
Landing on
and
the
it's
moon.
like, yeah. And it's like, yeah, we're going to see that again.
Yeah. We're finally past the 90s and early 2000s slump. That was like a horrible slump.
Well, I mean, I don't even know if that's fair, because I think one of the things that really strikes me about what's happening in AI is that it feels like it happened kind of as soon as it was possible. Like it wasn't like there was a time where we like, all the predicates were there and we were wandering. But one of the prerequisites for training these AI models is you need the internet, because you need like 10 trillion tokens sitting there in a machine readable form that you can consume. And so humanity
also some pretty good semiconductor
R&D. So you needed the semiconductors, which was developed by gaming. I mean, really, it was gaming, crypto, all kinds of stuff. Like the forces there that created the GPU were strong and robust, and there were multiple of them. But then you also needed the internet, and then you needed humanity to sit there for 20 years generating tokens, kind of taking the thoughts out of our mind, putting them into machines so that you had this machine readable resource that you could then use to fit things. And really, as soon as you had that, we figured out the LLM. And so this is...
Though even without that, even without the tokens, you could have like the game playing type RL model from DeepMind and others. So like if we did not have the tokens, we probably would have been able to go, in some, like I think it's a lot more driven by Moore's law than.
I think that for stuff like modern LLMs, I think that the tokens are important. But I mean, we did, right? Like AlphaGo happened first.
Totally.
And so the self-play was figured out first, and then the transformer.
And there'll be even greater cases of it. I actually kind of think that LLMs right now, and the hunger for their improvement has taken over a bunch of the cycles that would have gone into self-playing type of results like AlphaFold. And so I wonder what range of things we would be playing with right now if our main modality was not like the chat conversational.
Yeah, I mean,
system.
people. I think you can say like, oh, like have transformers and LLMs, like this one paradigm like sucked the oxygen out of the room. But I think the reality is it's just like way more oxygen.
Yeah,
like the total spending, the total amount of talent, the total number of companies is just like massively larger than it was 5 years ago. Like 5 years, like the people that are working
3 or 4 times the entire R&D spend of the US on like non-defense.
Yeah, and so it's like you could say like, oh, maybe we'd be exploring these other architectures if it wasn't all dominated by the LLM. Yeah. But like we are exploring the other architectures, and those are as big now as people were actually doing on the scaling hypothesis 5 years ago. And so I think you're getting all of that.
It's going to be a pretty interesting
and
2030.
BCI is like, I think there's one interpretation of, well, there's 4 or 5 highly funded big companies, and they're going to like run like that's like they're going to kind of drive this. But I think that it's going to look similar. I think in 5 years, as BCI really begins to translate and more of this is really developed, there will be hundreds of companies. There'll be a whole ecosystem. It's not like none of these things end up as there's like one player in a really robust space.
Let's talk about company building and broad R&D. So you, and kind of like driving breakthroughs, basically. I tend to give a talk about Fast R&D, and you're one of the examples that I often give. So it's basically lessons from you, Elon, Sam, and Steve. So to set this up, Patrick Collison has this great post called Fast, where he collects a set of examples of people quickly accomplishing ambitious things together. And he has examples like the Alaska Highway built in 234 days, the Empire State Building built in 410 days, JavaScript built in 10 days, Unix, the first version in 3 weeks, the iPod, 290 days from concept to ship to customers, which is insane, right? Like a whole device from Tony Fadell joining Apple to the first iPods are shipped to customers, 290 days, under a year, like amazing. Now, tons of R&D, tons of companies just move excruciatingly slower than that. Sometimes it takes many years to get anything out the door. You've been able to do many generations of devices, multiple devices, different platforms. You like have a fab. There's all kinds of fast R&D approach that you've been able to do. So why does going fast matter?
So for a lot of this type of like research-driven innovation, it is basically unknowable how long it's going to take. So you can't, like your ability to plan out milestones, like you can't like put it into your task tracker and be like, oh, well, in like December we'll do this, and by February we'll do this. It's like totally different than like building like many other types of things. The only thing that you can really control is the rate at which you learn. And so the how long your iteration cycle is like, it has a hugely determinative impact in the outcomes. And so because you can't see years or even like many quarters in the future, you're just limited to like how fast can we learn? And then we apply resources to things that are making progress and are working, and you like reallocate resources away from things that are getting stuck until there's either a breakthrough or you have a better idea. And so that is like a central management mechanism for this type of research. Now I've learned that like there's really no substitute for vertical integration for many of this stuff. And in some sense, it's actually kind of like a market failure. Like the fact that we need to have a lot of our own stuff in-house, including, like you mentioned, a MEMS fab, but also animal research and also a lot of like chip like design. It would in many ways be nicer if there was like a robust ecosystem of companies that were really sophisticated and could move fast and you could just like buy it from. Because then we would raise less money, we'd have a smaller org that was easier to manage, that could be more capital light, we could take less dilution. And in some other parts of the world that we should probably be paying attention to, like they can do that. Like you can have these smaller companies that are part of an ecosystem that you can just like order this stuff. And so in some sense...
And that's kind of like what the US was like in the...
That's what the US was like 60 years ago. And so now there's, I think like, there have been a couple of really successful examples of vertical integration making a huge difference in these companies having all this in-house. And
probably the first example of this in a serious way was Apple, right? Like where vertically integrate the entire process of manufacturing, building all pieces of the product, selling it all the way to the customer, and so on.
Well, I mean, Apple famously partnered with Foxconn. I mean, so I think actually, like that's... I don't know if that's the right example, because like they made a choice like TSMC and Samsung and Foxconn.
That's true. So I guess that they were still like doing a lot of things that like the level of you basically cranked it up a notch. Several notches. So back in 20 years ago, people used to say Apple vertically integrated a bunch of stuff. They were still building on top of the semiconductors for other people. Eventually, they now have Apple Silicon and whatnot.
Yeah. So that's true.
They're still not making their own stuff.
Yeah. So certainly, So they're taking advantage of that very sophisticated Asian supply chain. But yeah, I mean, they make their own silicon. I mean, the real magic of Apple is the deep integration kind of all. Like they really care about how it works from end to end. But they still use, like even for Apple, they use contract manufacturers. They don't manufacture internally. But the
do you think that's going to be humanoids in like 5 or 10 years?
I think humanoids are one of the places, manufacturing is one of the places where humanoids make the least sense, because you've got, like, you can...
Oh yeah, maybe not humanoids, just robots.
But yeah, I mean, there's tons of robots. I mean, like automobile manufacturing lines are incredibly automated. Yeah. And I mean, building,
But we still haven't been able to do certain things like wire harnessing and like a whole bunch of other things.
Yeah, totally. And I think some stuff like that, like, I think, well, in fact, I definitely, like, I'm a believer in humanoid robotics. Like, I think like, there's a meme out there that like humanoid robots are stupid. They should always be more neuro stuff. But like realistically, the world is built for humanoids, and the more you can fit into that interface, the better. But in the manufacturing environment, where you're going to spend $1 billion to build a manufacturing line, there is going to be more specialized stuff. But I think that people are underestimating how much even relatively basic robotics with really smart software and pretty good sensors will be able to do. And so I think that actually that is really software limited. And it's like a weirdly contrarian opinion. Like you say this to some robotics people and they're still like, oh no, like hands are bad and like these sensors are bad. You need more motor bandwidth and all this stuff. I'm like, I don't know, man. I think that you could take like basically like a Roomba with a sufficiently smart model and it will impress you with what it will be able to do. But a lot of the robot controls problem is just not solved well yet, right? Like there's all kinds of like easy dexterity type things that robots just fumble at. And so I think people hide behind it's just the hardware is not good enough because the software is just so bad. Yeah, exactly. And I think it's the easiest bet in the world to bet that the models get better. But on the vertical integration thing, there was one thing I would say, which is like in some sense it's kind of a failure. But on the other hand, the other thing that it enables you to do is if you really want to innovate, it is if you're limited to things that you can piece together that are otherwise commercially available to buy, you will always be a little bit limited in like how novel a thing you can build. Whereas if we can say like, oh, like this is the arrangement of matter that we want. I want to put these atoms in exactly these places, and I'm willing to void the warranty on a $2 million fab tool to like place those nitrogens exactly where I want them. Like that just allows deeper innovation, but it's very capital intensive.
And so one part of the approach is how you manage the team. One part of the approach is vertically integrating, maybe on the team and how you organize. You mentioned this kind of like control loop of limiting the resource spend that you go into things, trying to maximize the learning rate. Give us some like a concrete sense of like what does that look like? Like how fast is fast? Like what does it mean to drive a project quickly?
I mean, some of this you get a sense of what's fast, and I think people, it's a totally reasonable question. Like, how do you know? And I think one of the questions I ask in people I interview is like, how do you know that you're good at what you do? Like, what evidence do you have for this? And it kind of depends on the context. For some of these things where it's unknown how long it can take or should take, I think the thing that all you're really left with is like, at the end of the day, we just want to be convinced that there's nobody else on earth with our resources who could have done it faster. And in this case, like competition can be great because I think like nobody sets a world record running an open lap. Yeah. And you don't really find out what you're capable of until.
And as soon as the 4-minute mile got broken, then a bunch of people
did it. Yeah. And so it's like you never really find out what you're capable of unless you feel that pressure to deliver.
So, but often a lot of groups don't describe at all like you maybe see some of the public timelines and whatnot, but in terms of like the whole host of small little projects that a big project breaks down into, how do you like keep the internal clock cycle really fast? I've just seen so many. This is kind of like large organizations just start bloating, right? Like this is what happened to like, all of the major government contractors that got really slow, like the major tech companies. Like how do you avoid this kind of ossification or just like this bloat?
Yeah, I mean, small teams that are people doing things. Like there's like, all the prizes are for making things that work. And so you want small teams of people that are like with their own hands. There's not a lot of other managers. There's no people sitting around whose job is just paperwork, unless it's like quality and regulatory where the job is literally paperwork, which is also important. But I think when we interview, like people ask like, what do you look for when you interview? And I think there are two things that I look for, and they're not the hard skills. The technical team that they're interviewing for will determine if they meet the threshold of hard skills. But even then, like often that can be taught. The two things that I care about the most, which I found are the least teachable, are like an intrinsic sense of urgency. Like, do you just like, does it matter to you that this stuff happens sooner? And then just judgment. Like, do you make good decisions? And my central measure of capacity is like, how successful have you in making your life look like you wish that it were, for whatever that means? Because people have different interests and different ambitions, and some people want like maximum free time to spend with their kids. Other people want to be at the very top of their field and are willing to make trade-offs for that. But whatever it is, like how good are you at making like your life look like you wish it were? And by the time that you've gotten to like your mid-career, there should be like visible evidence of this. And so the sense of
why instill a sense of urgency when you can just hire for it?
Oh, yeah, and I mean that's like, and it's just like tough. Like that's tough to teach.
Yeah.
Sometimes I've seen smart people that were just like in the wrong environment or had a different cultural example, but they like knew that they wanted something faster. But definitely if someone is happy on island time, then like we're not going to convince them otherwise. Yeah.
Yeah. Do you do kind of like a Netflix style, kind of get very clear about that really quickly early? Like how do you approach that in the interview process to be able to like clarify to candidates that, the clock speed that you sort of expect in the organization?
I mean, I don't know if it's definitely a thing that gets talked about in every interview. Like, how would this person fit in here? I don't know that there's like a bright line rule or guideline that you rely on, but it's something that everybody is looking for.
And how does the team kind of kind of embody this? I think historically, lots of organizations have degraded in part because the team just kind of, if the incentives are not set up right, or if they don't have like this very strong intrinsic motivation, then just everything starts taking a little bit longer and a little bit longer.
Yeah,
and just quickly degrades.
You got to keep an eye on this. Certainly keeping an eye out for evaporative cooling. Like A players hire A players, B players hire C players, C players. It's like even a massive explosion. And then your best people get like disenfranchised and they start to leave, and then you've got a real problem. And so like being very paranoid about that is important. And so I'd say like
can you clarify that a bit? Like in the A players, higher A players thing, which comes from, I don't know, early Silicon Valley perspectives and so on. I've often thought that like that model of like just these three buckets is like a vastly overly simplistic view of, you know, a deep exponential where skills are dramatically, there's like an enormous ladder of skills, right? Like
definitely.
And so how do you, but I think there's something qualitatively different, which is you could have people that are deep mastery level on some field, and yet they don't have the quality that like the Silicon Valley A player thing meant, and that maybe you're approaching with a sense of urgency thing and so on. Like, how do you kind of define basically what does an A player look like when they're very early in their career, or where they don't yet have the degree of accomplishments that you can like clearly, you know, look at it from like a, you know, LinkedIn profile perspective says like A player through and through. Yeah,
I mean, I think like it's just like how intentionally have you been in, like, I think an early marker of this is even early career, you've gotten through 20 something years of life, or like 18 or something, and how intentional were you through that? Like there are people who, it's like one thing I like to do is you'll start at just kind of like, where did you grow up? Where did you go to high school? Where did you go to college? What did you do after that? And you're always looking at, like the thing I'm looking at is like, did you make decisions, or were you just kind of swept along? And many people are just kind of swept along. And so the first thing that I look for in these junior candidates is just like, have you made like intentional decisions? Did you end up in a place that you kind of meant to be? And
do you think that's a personality trait, or is that kind of learned? Like, have you encountered people that maybe were swept along over time and then started taking agency, or vice versa, like maybe had a ton of agency and then just that sort of broke down?
I mean, you see all kinds of patterns, but yeah, it's like you're looking for high agency people, and you're totally right that it's the like the very best people are like much more dramatically effective than the average person.
I think it's like really not well appreciated by people globally, especially even like a deep knowledge work domain where the leverage is just so significant. In Silicon Valley, people talk about it in terms of like a 10, 100, 1,000x type of things, but these are like deep exponentials. You're getting into the 10 of 1,000 or 100,000 level of impact, where like one person in the same year of time will be able to have like this incredible degree of leverage over the same problem space. And it really breaks down into like typing on a keyboard. It's like the same, you know, mechanical range of.
But it's not that they're producing like more lines of code, or they're producing more PCBs.
It's like the right bits.
It's the right, yeah, exactly. And so in that sense, it's not even, it's like tough to think about it in terms of like 10x or 100x or whatever, because it's not like they're even, like they often do work long hours, but it's not that they're moving faster in that sense. It's that the things that they do just work and unblock things, and there's kind of no amount of time that others could have spent on it where they would have found as good a solution. And I think like one of the biggest mistakes that really smart engineers make is like highly optimizing a thing that just shouldn't exist in the first place.
Yeah.
And like as a famous saying out there now is like the best part is no part. Yeah. And this is definitely true. I mean, I think the best systems are very simple. Those are also the most reliable. I mean, the closer that our products get to a single block of covalently bonded matter, the higher performance, the lower power, the better they'll be. And this means that you have to find ways to really simplify it to like whatever the minimum physical thing can be. And that like simplicity is like not trivial. And so the best people, when you think about like, oh, like someone is 10 times as effective, that doesn't mean that they're writing 10 times as much code. In fact, they might write even half as much code or a third as much. Because the thing that they come up with is fundamentally simpler and in that more powerful. Yeah, exactly.
Yeah. You emphasize judgment and good judgment. I have also found that this is extremely critical. How do you, you kind of like described interviewing for it, and kind of looking at people's judgment and decision-making across their life. What are some of the ways that like it shows up in I don't know, when running a team? Like what does like good judgment look like in a team?
I mean, do the things that you propose, like do the ideas that you have tend to end up working? And we give resources and responsibility to people who, like, when I see them get excited about something, I'm like, this is probably going to work and it's probably going to be cool. And then you also know that it's like, oh, these people have pushed for things, but they've been dead ends or they haven't worked or something. And so it's like, you know it when you see it. And
how do you encourage exploration on things that where legitimately you might have to pursue a whole bunch of dead ends before you find like the right one?
I mean, you shouldn't really need to pursue that many dead ends, or when you do it, it's fairly intentional. Like sometimes, like in practice, it's not like this whole idea of like, oh, you throw away 4,000 prototypes. Like it doesn't really work that way, at least the stuff I've seen. But there might be a thing where you're like, so for example, in the retina, we thought that there'd be some way to get a visual signal into the brain past the photoreceptors. For that, you've got kind of this 2x2 matrix of bipolar cells, optic nerve cells, optogenetic, electrical. You could extend that. You could do sonogenetic. You could do other things. But for us, we're like that. You got a 2x2 matrix, and we're going to do a survey of all 4 quadrants, and we're going to like exhaustively explore the space so we understand the trade-offs of all 4 quadrants, and then we're going to narrow in on the things that we think are worth like exploiting further. And so sometimes you want to do like a parameter sweep of like what is the space, and you can understand the space in some cases almost exhaustively. But from that, you then want to narrow this down, and you don't. Like if you're kind of constantly like doing a lot of effort, like if we get set by 6 months on a project, that's a big setback. Like that doesn't actually happen that often.
Tell us a bit about how you manage time in the company. Like how do you set goals? How do you set timelines, deadlines?
I mean, it's tough to set arbitrary deadlines. I mean, you have it's really smart engineers and scientists don't really like arbitrary deadlines. If I come along, I'm like, you got to do this by this date. They're like, why? And I'm like, because I said so. They're like, that's not convincing. That doesn't work very well. Now, in some cases, you have some exogenous deadlines. So, for example, there could be a big opportunity that where if you have something ready by then you know that you'll be able to get people to check it out. Or there's some other dependency where if you're not ready by then something else will be blocked that could have proceeded. And nobody wants to be the bottleneck. They kind of all want to hold up their end of the bargain and have their parts ready by the time it needs to be integrated. And so you have these kind of mutual bottlenecks where the chip people don't want to block things, the animal people don't want to block things, the probe people don't want to block things, the cell people don't want to block things. And so they'll have a sense of it comes together. And then in practice, there are trade-offs you can make in each of these so that you can ship something. And then you can make each part better over time. You just keep iterating. It's like a high rate of iteration. The first version is not going to be perfect, but you want to get to some threshold of performance so that you can start making those trade-offs and be like, okay, this feature's not important. Like you can have a higher noise floor in this chip, or you can have a smaller number of channels, or you could have a cell that doesn't have some particular phenotype, or some thin film. We're going to go with 2 layers instead of 4 layers right now, because that's the trade-off to like keep the thing moving. And then we're going to get that back on the schedule next time. But
it still requires like a great manager to set those pick those concrete externalizable things.
This is what I do all day. This is what the leadership here does.
Because I think otherwise left to its own intuitive devices, teams will just expand the timeline and kind of like erode erode time, and then things will just take a lot longer. And there'll always be like really good reasons for doing it.
There can be. I mean, hopefully at the like that team level, there's still people want to ship things and they want to get things out, and they're able to do that in a decoupled way. But I mean, as part of culture, you need to have this sense of paranoia of like, we don't know how long it will take. We don't know if we'll need to respin a chip. We don't know if we'll need to do another surgery, or we don't know if we're going to need to generate some more evidence. And at some rate, like you do eventually run into these absolute limits of like, you can only raise some amount of money at some price, at some terms, and then you're out of money and everybody goes home. And
you thought you were going to be able to raise money in 2 years, and the economy like fell apart.
It changed,
You can't.
And so you have to have this paranoia that you're like, I don't know exactly how long this is going to take. And because of that, I have to just go as fast as I can, because that might not be enough. But at the end of it, you want to know that there's nothing else you could have done.
But there seems to be a great quality of really great founders is that they are able to pick the right way, like the right threshold of maintaining this extremely fast pace and externalizing the deadline. So, for example, one of the famous stories on this is, the iPhone keynote, the iPhone launch keynote is like this magical moment in Silicon Valley history. Like people tend to reference it a ton. Not many people know the iPhone was built in around 2 years, roughly, like from deciding to do it to then like shipping the thing, or deciding to do it and announcing it at the keynote. And Steve gets onto the keynote, describes the price and the date of shipping, and the manufacturing team learns about this at the keynote. And so they have no idea that they need to like ship this device in 6 months and the cost structure that they need to fit. And they had, of course, like ballparked it probably, but there was like not an agreement, not a plan. And now they have to like scramble and then do this within like 6 months.
And I think like part of what made Steve drop, like that somebody like that is like knowing what is possible. Yeah. And in some sense he's making it up, but part of what makes him like so special is that he knew what the bounds were and that they could do it and could be pushed to do it, and then was right. And I think it's tough to know. I think then like there's lots of other founders kind of model on that and will be like, well, like he was a dick, so like I can be a dick.
Right.
And it's like you're missing the point. Like it's not about that. Like the thing that was
it's like
the thing that was
wrong
great was the revealed judgment. Yeah. That he was like right about these things. And then the being a dick part actually like it wasn't a feature. He was successful despite that.
Right.
And that's not, you don't.
Yeah. I've been wanting to write an essay called like Cargo Cult Founders, where it's like they learn all the wrong lessons from like great founders and then forget like to learn the really critical ones.
Yeah. And I mean, to be like, people have worked with people like, I'm not perfect. Like you care a lot. You want to move fast. It's a high stakes, high stress environment. But at the end of the day, like it's not about like those things are still to be overcome in these like incredibly stressful, incredibly high stakes situations. And
yeah, there's like a deep unfortunate thing about being a very strong founder, which is that just the demands of the technology and the product and the market and the people and the team and so on just massively compress the timeline that you have to like really care about a range of things. And so you can try extremely hard to not be a dick about a bunch of things and yet like come off like one at various points in times. And so like this is like a hard balance. Many people do it way better than others, of course. Like certainly Steve had lots of examples where he just did not need to be the kind of jerk that he was. And so many people do it better. But at the end of the day, like you're just going to compress the time that you have to be like a human with other people.
Yeah. I mean, this is part of the trade-off of getting to work on like the critical path of civilization. Like the reality is the stuff that gets done here is like it matters and it changes the world. And it's a privilege to get to work on it. And it's a lifestyle choice that is not for everybody. Yeah.
And I think that's something that maybe, I think Silicon Valley is probably a lot better about this now than it was in the past. Like people are much more aware and self-selecting into a bunch of this. And I think this is where like the Netflix culture of, good performance gets you severance package type of mentality of saying, hey, no, like we're really trying to build this athlete level team here and we're trying to win the Olympics of business. And like that looks a certain way. You have to self-select into that. And if that's what you want to do, amazing, great. If that's not what you want to do, that's okay. But like this is just like not the right place.
Totally. Yeah.
Deadlines though, you don't have the ability to externalize as many deadlines because you have to be a lot more private about everything. How do you set deadlines like that? Like, are you able to kind of like commit the team down a path to kind of like force things to happen?
It depends. There's always other things that we're interacting with. So like I said, like there's these mutual interdependencies where you want things to come together at some iteration cadence. And so that's like, people don't want to let their teammates down. And so they're going to make sure that they don't block them and make that other work a waste. But then there's other things like chip tape out dates. Like there's like shuttle runs that like that's a TSMC date. And if you miss it, then you're going to wait 2 months. And so like you're going to make it. And so there's these other things like that you get attached to.
You also use like these great internal demos of being able to demo, have like a clock cycle to the company where you demo certain things on a cadence and like just things have to be good for that demo period.
Yeah, exactly. So we've done these about twice a year since the beginning of the company where we don't really have board meetings, but we invite the investors, we invite the whole company, and then we organize like an hour and a half presentation of just like what is our progress since in the last like 4 to 6 months. And that's really as much for internally as it is for updating our investors. But it's like every once in a while, like the story is complicated. There's a lot of moving parts. You should organize your thoughts, show what you have to show for yourself. And for some of the employees, especially with like how we've been growing, they don't see the whole story put together kind of end to end because they're focused in on their part. And they know that they've been working on like the lifetime testing of implant packaging, or they've been working on new chips, or they've been working on some other like part of it, and then they see the whole story together, and that's a morale building experience for the team. It allows us to compact the story and make sure that what we're doing is sensical. And because there's these spinning blades of death every 6 months, it kind of creates this forcing function of like we're gonna have something to show for ourselves.
I love it. It's like a whole company board meeting structure. Because board meetings famously have been used as this forcing function for the exec team to actually think through things carefully and report to a set of stakeholders that then get to reason about things and so on. And so many teams use board meetings as like a forcing function for high quality thinking across the board. But that often tends to happen only with a small fraction of the company or stakeholders. And if you do these like larger demos with the whole company and like the entire stakeholder set, like that just gives a like a shot in the arm to the whole group.
Yeah, I mean, getting that whole organization aligned is like one of the central challenges.
Yeah.
Like the idea of the company can be perfectly formed in my mind, but if that's not conveyed to the like 200 people that are otherwise touching it, then it doesn't really matter. And yeah, we've been fortunate where our governance is like relatively simple, and we can act with high conviction very quickly. But then aligning the rest of the company to that is, I think one of the lessons that I learned early in my career was that these companies are really human organizations, and you can usually get the technology to work. But aligning and motivating like hundreds of humans to do anything in the same direction is not trivial.
Yeah. How do you think it's going to start changing as AI systems get good enough to start planning and managing entire swaths of knowledge work and then eventually teams?
Yeah, I mean, so I don't know. I mean, ironically, the company our science is kind of architected around. We've got this internal software tool that we run most of the company through. So basically, all of the information that the company generates is in this internal tool called Helix, and like all of our purchasing, all the animals, all the parts, all of the meetings, like. It's a system we built in-house. There's just kind of a contrarian bet early on. I mean, I just saw, you hear all these stories and you see these things secondhand of like the power of internal tools at early Facebook or at YC and others. And I've used a lot of ERP systems and other tools like that, and like nobody likes their ERP install. And so I think
because they're solving for like a common denominator sort of user, not.
Yeah, exactly. It's like it's this category of software that seems to resist like generic solutions, but when one company grows up around a piece of software, that it can be very powerful. And so because it's all in one place, like you can expose a lot of this to AI agents. So like, for example, all of the meeting there's a note taker that joins many internal meetings, takes notes, gets them in Helix, and then people can chat with it and be like, hey, like what's the status of this project? And it can like read all the meeting notes and give you a summary.
Can you connect it to like, I don't know, project management software and then like figure out like what's shifted? And
I'm sure like down the road, there's like a ton. I mean, it's in like, there's some parts that are really sophisticated. Like every dollar the company spends flows through this thing. On the other hand, there's like an endless wish list of features that like are not a high priority to add.
Automatically schedule a new fab run?
Someday, yeah. I mean, I joke that like the next CEO of Science, I want to be an AGI. Yeah. And I'll know that we're getting there when kind of all of the control surfaces and all the information required to run the company are there. And I'm just like hitting like accept. Then maybe like 2035, be able to delegate that, and then I'll get to go back and do the fun stuff.
And you'll have the Biohybrid by then, right? So you'll be able
something
to
like that.
Talk. Maybe let's talk a bit about you as an individual. Like how did you grow up and become modern Max Hodak? Like when did you first get into science and tech? Like how did you what inspired you? I want to kind of get your story.
Yeah. So I started programming when I was really little. My parents told me that I sat on the floor of a bookstore and cried until they bought me a like Learn Q Basic or something book. And so I like from the time I was like a kid up through being a teenager, like the compiler was not especially concerned with how old I was. And I was into science fiction.
When you say really little, programming in what years,
I don't know exactly. Like I think I started with this when I was as little as 5 or 6, and awesome. I became like a good programmer when I was an early teenager. I was kind of always around it. Like my dad knew how to program. He had an undergrad degree in aerospace engineering. My parents are kind of in business, but I grew up building model rockets and having exposure to STEM. Mm-hmm. And I forget. I mean, one of the big inspirations was definitely the movie The Matrix, mm-hmm. where I think one of my personal ambitions is to disappear into the full dive VR, never to be found. Mm-hmm. I think the atoms are really annoying to work with. The speed of light is low. Earth is small. Like there's real estate is contended. Yeah, I mean, like if the world of bits explosion. Can be whatever we want. And so I think there's something very inspiring about that. That one of many potential missions. But through that and through other things, I got really interested in the brain and I kind of spent a lot of being a teenager reading about and learning about the brain. Are
these like textbooks or sci-fi or
textbooks, sci-fi, all of the above. I remember when I was in high school, I discovered there's like one book that stood out to me called The Biophysics of Computation by Christoph Koch, who is just like the brain is extraordinarily cool. And this is like, and the idea of being able to engineer that is just such a transcendent goal that if you can really do that, I think that, sometimes I think like, AI, my life would be easier if I had gone into AI instead of biotech, but people have figured that out. BCI remains to be solved. I think there's some important things there that
we need to run a portfolio approach here.
Need a portfolio approach. All go. But I went to the college that I did. So I have an undergrad degree in biomedical engineering from Duke, and one of the reasons I went there was because at the time one of the best labs in the world doing brain-computer interfacing in monkeys was there, Miguel Nicolelis's lab, and so I talked my way into that lab freshman year, and when I showed up at Duke as a freshman, I got matched with an advisor. They asked like, "Oh, is there any like researchers that you want to work with?" And I told them that I wanted to work for Miguel, and I was basically like rejected. They're like, "No, he doesn't take undergrads. This is like, only grad students and postdocs. He's in the medical center." And then I figured out that there was a chemistry course. There's like a seminar in chemistry that would place you in a lab, and I used that as like a backdoor to sneak in. And they took me as part of this like it's not a chemistry lab, but I got in through this thing. And then that was really where most of my education in college happened. Like I spent most of my time working in that lab. That was also where I met a bunch of people that would later turn into some of the Neuralink co-founders. So Tim Hansen was a grad student and then postdoc in the Nicolelis lab, as was Joey O'Doherty, who's now one of the senior BCI engineers at Neuralink. And in fact, I remember what later, like a decade plus later, would become the Neuralink surgical robot. I remember the first time Tim had this idea for building like a neural sewing machine, and he ordered this old like CNC. I forget if it was a pick and place machine or a CNC, but whatever it was this like extraordinarily busted, like available for $1 on eBay plus $400 in shipping thing that showed up. That then over the following like 18 months, he turned into a very early prototype of this like neurosurgical implantation robot. And then they ended up moving out to San Francisco, ended up becoming postdocs for Flip Sabes, who then was part of the Neuralink founding team later. But yeah, I mean, that lab, it was like a formative experience.
There are these like very special labs sometimes in some universities that end up crafting the people that then turn into the people that then generate the whole field. This happened a few times in computer science and specific fields, like all of graphics, for example, came out of like one lab, or the beginning of the graphics field came out of one lab, or like AI came out of like one or two labs.
Yeah. And Duke 08 to like 12. I mean, there's a lot of high profile alumni there, but there's like, it's really overrepresented in Silicon Valley to some degree. Like Fred Ursum, Blake Byers, Zach Parrott, like me, a handful of others. I don't know what was in the, like Harvard, Stanford. Yeah, that makes sense. But then there's this whole group, especially in biotech of like Duke from that era that ended up being super overrepresented.
How much did you learn in the university from the university itself versus just getting connected to the relevant people in the relevant lab?
I was not I was not really into school. For my last years of college, I actually ended up working out in Silicon Valley and commuted to college because I went back because I wanted to keep working in the lab and that was interesting research, but I kind of showed up to exams and turn in problem sets, and otherwise did not spend that much time thinking about the coursework. I each semester would stuff all of the labs into like either the first or back half of the week and spend the rest of the time in California. I don't know. There isn't really advice in that.
Yeah, I think it's just like a trait of how people go through college and so on, right? I mean, we both know a number of people who have chose not to go the university path and ended up now do incredibly breakthrough R&D work in a range of places and are effectively self-taught, or like they found ways of learning the relevant information.
I did really feel like I needed to finish the undergrad degree because I'm enough of a dropout without having a PhD.
Yeah.
Someday, if the stuff that we're doing is really works, I'll fix that at some point. But but yeah, I mean, most of my education happened outside the classroom.
Yeah, I think in your case, in neuro, you can't be a university dropout. You have to be like a PhD dropout.
Something like that, yeah.
And then what about after university? So you, from there, I guess, went to Transcriptic?
Yeah, so when I graduated from college, I thought what I want to do is start a BCI company. But this was 2012, and I thought it would take at least $100 million. And this technology was at least 10 years away from clinical translation. And I didn't have $100 million. And so the choice was basically like go to grad school, in which case I could spend 6 or 7 years in grad school, and after which be kind of a postdoc that still didn't have access to $100 million that nobody really cared about. Or I could come back, move out to Silicon Valley, start a different company that I thought was more accessible with the kind of resources that I could raise at the time, and really learn how to build companies. And there was another idea that I had that I thought was pretty good. In addition to working in the Nicholas lab, I also spent a little bit of time in a synthetic biology lab where I'd had the experience of kind of going into the lab to press a button on a machine every 3 hours for 3 days to take a growth curve of this bacteria that I was engineering. And I was like, there's got to be a better way.
Yeah, it is astonishing.
And to do that, you also needed like all this lab space and millions of dollars of equipment.
Yeah.
And so this was around the time that cloud computing was really starting to happen. And so the idea just felt like very obvious at the time, which was like, what if instead of having your own lab, you have a cloud lab? Mm-hmm. And you couldn't simulate this stuff. You needed a physical laboratory with a bunch of robotics. The idea is we'd have a set of APIs that scientists could use over the internet to run experiments. And one of the things that made me think this was possible was I'd figured out by this point that you could buy lab equipment like really surprisingly cheaply at auction. And so for the $10 or so million that was accessible that I could come out and raise from Google Ventures and some others, you could get started on that. And so that became Transcriptic. And from 2012 to kind of end of 2016, I was founder and CEO of Transcriptic. We built a small business there.
So it was kind of automating all of the flows of a specific synthetic biology workflows.
Some parts of like cell and molecular primarily molecular biology. And
this is like automating it through like robots, or is it just like, how much of it was like software around existing machines versus robots on top of the machines? Or
it was existing machines and custom like robotic arms. Like we had we built custom refrigerators and freezers and incubators and custom like transport systems. So the standard unit of the device here is this thing called the microplate. Mm-hmm. And so we made some custom robots for like moving microplates between devices. And then all of the software is custom.
Yeah, by the way, this is kind of like what TSMC and others look like today, right? Like with like the wafers being
with wafer handlers, robots. Exactly. Yeah. And so Transcriptic ultimately did not revolutionize its industry. I think we kind of made some key mistakes there. That was definitely on hard mode. But early on, we were selling to academics because I was a student. Like that was what I knew. Like I knew these academic labs. I was not connected to big drug companies. But the automation biology, it is good for like if you need to run an assay 10,000 times or 100 times, it can do that quite well. But biology is still like really pretty finicky. This is not. It is not the case that you can just like write your protocol out as Python and then run that and have that work the first time. There's like a bunch of high touch interaction there. And with academic customers, if you gave them the option of like their protocol could be twice as complicated, but they'd save 20% per sample, they'll do that every time. And that just like it turns out to not really be a good fit for this type of automation. And so after a couple of years in, we'd really figured out that where the business was in serving pharma and kind of conventional drug discovery. And we eventually got some big contracts there. Like we ended up with this huge contract to run this $100 million Eli Lilly facility in San Diego. And that business screwed over to like pretty substantial revenue. The year my last year as CEO when I stepped down to kind of co-found Neuralink, and ultimately it did not live up to its potential. There are elements of that business that I think should be tried again at some point. But still to today, I think one of the structural things that I got wrong there, or just wasn't in my worldview at the time and is only kind of now becoming possible, was biology doesn't happen in milliliters. It barely even happens in microliters. Biology happens in like picoliters and nanoliters. And microfluidics has been around for a long time, and people have talked about building like lab on a chip for a long time. And there are lots of lab on a chip, like single purpose things. Like there's lots of ASICs, but there's no lab on a chip CPU. And that's been a very resistant problem that a lot of people have thought about. But things like modern like DNA sequencers or there's like lots of things like that run on microfluidics. And whenever you can scale down, your automation to that, to deal with biology on its length and time scales, things will get more predictable. And so I would approach it very differently if I were to do it today.
As you mentioned, so you stepped down from Transcriptic to found Neuralink.
Yeah, in summer of 2016, I got introduced to Elon, who already, I mean, when I met him, he already had the name Neuralink in his mind, and he knew he wanted to start this and was very concerned about what he saw on the horizon with AI, which I think has proved to be remarkably prescient. And I think he deserves a lot of credit for really like creating the modern instantiation of this field. Like without his bet on BCI, there would certainly not be the ecosystem and industry that exists today.
Yeah. Let's end on, what advice would you have for, yourself coming out of high school or college, or maybe not necessarily yourself, like just people right now staring into, 2025 with 2030 and 35 coming up. Like, what would you recommend, like, brilliant people out there be focused on?
Well, I think one thing to be very careful of is you've seen how like social media and like mobile devices have atrophied attention. I think there's a much more pernicious danger in copy pasting from ChatGPT, like atrophying reasoning ability. And so you have to keep thinking for yourself. And in fact, I think this is one of the central things that makes kind of having any interesting career really, really hard. If you cheat on like a test, then your grade will trend towards the average of the class. And certainly for startups, that would be failure. And so you have to do better than that. And the only way to do better than that is to really think for yourself. And it is actually quite hard to do that because by its nature, you'll have people telling you like other like objectively successful, smart people who you think are capable, giving you all this input. And nevertheless, you must pick things that make sense to you, even when you're alone in it. Because like you might be wrong, but you can't beat that ultimately. And as soon as you start delegating that, I mean, you can, in your judgment, delegate the judgment, but you still have to take kind of all cause responsibility for the results. And that the thing where it's just like, I can't tell you how many times I've seen something where like there's a consensus view or like really literally everybody has some perspective on something. I'm like, that doesn't feel right to me, but you're like, didn't I trust that? Because like, I don't think my judgment is perfect. And so how do I know? But ultimately you just have to do things that make sense to you. And then it will get revealed how good your judgment is. But that's the only way to get differentiated results. And I worry as we start offloading, like we were talking about earlier, like if you have your phone with you, your memory gets worse and your attention gets worse. And now you've got this possibility of offloading thinking that like, unless you want to be totally dependent on ChatGPT or Claude or Gemini, I mean, I think that's like that is like one of the AGI takeover scenarios that doesn't get talked about as much, where there's not like robots out hunting the humans, or not even like a single big agent that's like clearly running the world. It's just that all of the humans have totally delegated their thinking to the machine because it's producing better decisions than they used to have. And then suddenly you're just kind of being puppeted.
Well, hopefully you'll fix that by getting the Biohybrid in place and then other next generation devices.
So you have to be really thoughtful about how you integrate that with your own decision making and your own thinking.
When people are just starting out, sometimes it's kind of hard to remember how hard certain things were in terms of how do you build your first project or your first attempt at a company or raise your first money. Like
totally. And the advice that you get from experienced entrepreneurs, I remember this clearly because I'd go ask people like, how do you raise money or how do you organize a team? And they're like, well, you need to have like a really clear vision and you need to have like a good culture. And I'm like, okay, but like, how do I raise $1 million? Yeah. And that's just like having a good culture is not practical advice. And like there are tactics that you can learn and there's like various things that are practical, but then you get to like later on, you're like, oh, that actually was the important thing. You actually did need, like you're saying, like, how do you make sure that you're always moving as fast as you can and that you have these short time constants and you don't just like bleed out by a death of 1,000 cuts of these small slips that people don't take seriously. It's like the answer to that is culture. And in some sense, these kind of like are the answers. Yeah, but you need the more tactical specifics.
Yeah, there's a great meme, how do you draw an owl, which starts with like 2 circles, and then
you draw the owl.
You draw the rest of the fucking owl. So a lot of the advice is, hey, you start with the 2 circles, right?
And so the way that I've kind of characterized it, like the apprenticeship that I did at the company I was at before Science was invaluable because there aren't really generic principles of startup advice that just like if you hear the right like 1,000 words, you can turn the crank. It's it's like like a career is like a long series of decisions, and you want to be able to look at those fact patterns and make local decisions that are best for those fact patterns. And even if this looks like inconsistent over time, like it's like a situation that is like similar, but you look at the facts like slightly different, like you should feel empowered to make a different decision. But the thing that you want is that your filters are well tuned so that when you're faced with these things, you make high judgment decisions. And that is, like, I think, a different lens than like what are the key like tactics. It's like you just need to be good at making decisions, and the best way that I've seen for that is to this is really an apprenticeship. It's tough. Like, you can't really learn it through school. And I tried to do it on my own, and that was very difficult. And humans are very mimetic. And I think like the PayPal experience there's a whole cluster of Silicon Valley that they figured it out, and they did it. And that was like a really powerful founding moment, like culture that came out of that. And then, I, like many others, ultimately got some of that imparted by doing the apprenticeship. But these cultures are oral traditions. And the only way,
and also in practice, right? It's kind of like a Jedi apprenticeship sort of situation where like you have to like join the group and then like go take.
And they're tough. Like, I had the experience of it was like your best friend's birthday that you've been making plans for, and it's like you get the text, you're like, the plane leaves in 45 minutes, get there. Yeah. And the only way to like learn these things is to be trying to make these decisions like with jeopardy and stakes attached, looking forward with uncertainty when it matters, and you go through like a bunch of reps of that. And then you find out if you can learn it or not.
Do you have like a young Max style apprentice?
Well, we're fortunate to work with. Look, we still have a lot to prove. Like, I do not want to sit here and say like, I've worked for very successful people. I have friends that are very successful. We have a lot to prove, and I think we should acknowledge that. And so I'm still like we have a long way to go. But yeah, we're fortunate to work with some really talented teammates, including some others that I hope like also like receive the oral tradition.
Yeah. Let's finish with any recs for either like very inspiring sci-fi or people to read, or books, or maybe underrated sci-fi.
So Pantheon is great. Pantheon it's an animated TV show. Highly recommend it. It's on Netflix. I joke that it's actually a horror story about the extinguishing of consciousness in the universe, but people should go watch it.
Is that a spoiler?
I think a very mild one. Yeah. The Culture series, I think if you want to talk about like people say like, oh, we want to build an optimistic future, the Culture series probably best embodies that. And it's kind of unique among science fiction in that it deals with artificial intelligence. AI is kind of a tricky topic because as soon as you have it, it's kind of like time travel. Like, the story is only about AI or only about time travel. And the Culture paints a picture of like a far future humanity that is like fully elaborated in these ways, and is in some ways a utopia, but in other ways very complicated. And so many of the stories are told kind of on the periphery of the civilization, where they interact with others and they face these complex moral and ethical dilemmas, and you see how those get navigated even in basically utopian society. I also just love The Expanse and hope very much that Mr. Bezos decides to make the last two seasons.
Yeah, that'd be great.
Yeah.
Hey, thank you so much for doing this. It was great chatting.
Thanks for having me.
Yeah, thank you. Cool. I hope you enjoyed this episode. This is a new podcast, so we need your help to get the word out. Like, rate, and subscribe on your favorite platform. And please share it with people you think would find it interesting. Thank you, and see you next time.